It's great to be here, surrounded by my peers and my friends to talk about replacement. And it's great that I'm the last because you heard a lot of what I was about to talk. So quickly about me, my day job is general partner at the fund called NFX. We manage 1.4 billion and we do seed investment. And the great thing about being a VC is I can invest in my own companies and my own passion. And my passion is definitely longevity. If you go to nfx.com/bio, we wrote about it. We invest in that, we support things like that. And when I saw the science behind renewal, I was just mind blown. I thought it was the most impressive technology I ever seen that can really move the needle in longevity. So we have like a quick 1-minute video of the high level explaining what it is.
Human embryos created entirely out of lab-grown stem cells. No sperm or egg required.
For the first time, successfully creating a viable synthetic mouse embryo. And they did it with nothing but the mouse's own skin cells. It's projecting that within 5 years, we'll be able to take a patient's skin cells, revert them to stem cells in an already developed device, and then within a few weeks, produce any needed transplant material that is genetically identical to the original patient.
Scientists say it will allow them to understand more about those early stages, a widely understudied topic and one that could be helpful for humans.
Grow them in special condition and put them in this device for about 20 days, and they self-organize alone over 8 days into a whole embryo. And we can take these cells maybe and transplant them back to the patient.
Yes, so the research behind it was peer-reviewed, published in many papers. The last one in October last year. This is the human stem cell-derived embryos, day 14, already in the lab. We're at day 21. We'll talk about it later. My team always tell me, don't talk about embryos. We're not making embryos. We make stemroids, stem cell-derived embryo models. It's a model. We talked about replacement. And again, the initial thing is like nature have solved aging. 40 and 50-year-old people can make 0-year-old babies, right? So nature know how to, reset aging, and humans know how to do it, as we talked for cars and buildings, a combination of replacement and maintenance. So the entire story starts with Professor Yaakov Chana. When he was in MIT, he developed this, calling it an ex utero, or calling it an artificial womb is kind of too much. It's more like a bioreactor to grow embryos. Initially, and this was published in Nature, he took natural mouse embryos and grew them from 0 to day 13.5 out of 20. So 2/3 of pregnancy was captured outside of the uterus in this machine. The next thing he published in Cell, and I think he's going to win the Nobel Prize for this discovery, was the first time we could make embryos directly from stem cells. So we took naive stem cells in blue, split them into 3 populations. Some of them we kept as is, those were the embryos. One we pushed in red to become the placenta, in green to become the yolk sac. We co-aggregate those cells, we put them in this ex utero setup, and magically some of them became day 8.5, so almost half pregnancy capture outside of the uterus, fully synthetic embryos just from stem cells, no sperm, no egg, no uterus. Some data, this is a video of one of those embryos. You can see the heart beating. The blood islet with the first hematopoietic stem cells being developing, the initial brain cells. I think this is the magic behind the system. We know to go backwards in time using the Yamanaka factors to a very naive state. And some people say, why don't take those IPS and turn them to the cells and organs that you want? But the problem is, and what you can see here, this synthetic embryo and natural embryo, development is very, very, very complicated. So, and the magic here is just to create those embryos, and once we make them, we just feed them. Right? We just feed them, and then we ride the coattails of 4 billion years of development evolution to get all the cells, all the tissues perfectly differentiated. To show you how good it is, this is a single cell RNA data, single embryo, single cell RNA data. On the left, that's a control, natural embryo in the uterus, and in the right, 5 different synthetic mouse embryos. RNA-seq data above 95% similarity. We don't have any UF4 cells. We have all the cells we expect to see. You never get anything close to that when you try to differentiate from IPS. So obviously, the world has taken notice. It was all over the papers, and people ask, can you do it in humans? So as I showed you in the Nature paper, yes, we can. So different amount of cells, instead of 25 in mice, 120 in humans. It's actually slightly easier in humans than in mice. This is an important slide from the paper because below you see just images from textbooks of development, how cells should be developed, how embryos should be developed. and above is our result. So we have all the cells, all the structure we expect to see perfectly so far, perfectly developed. So on the right, you see a video of one of those synthetic human embryos. On the left, we went to CVS, bought some pregnancy tests, and it's so good that at day 8, we trigger them. It's a boy, it's alive. So since then, we started a company, raised around $9 million, though I think for this kind of technology, we should raise way more. We do a lot of experiments. There are many ways to get those 3 cell types and many ways to continuously feed them along the way. We were able to increase the yield from less than 1% to almost 5 to 6% of creating successful embryos from stem cells by doing a lot of work with different reagents. This is unpublished data, we got to day 21 and we're pushing this system forward. So why? Again, currently we're at day 21. When we get to day 35, 28, we get fetal liver and very potent hematopoietic stem cells that can be directed to the bone marrow to solve real disease, bone marrow failures, but also to renew the immune system. Day 40, we have hepatocyte, we have initial brain tissue that we can use. Day 70, we get gonads, and all the eggs women will ever create is created in the embryo state. And in mouse, we know that we can take day 8.5 gonads and produce mature eggs for women. So imagine that, you give us a skin cell, wait half a year, and you get as many eggs as you want. And then how do we push it forward? We need to solve technical and ethical issues. I'll show you some data around how we can solve both. Currently, we're rate limited by diffusion. In mice, we got to day 13.5, but we feed it through diffusion. So when the embryos grow, the stem embryos grow too much, we get into trouble. It's hard to feed them. And obviously, ethically, nobody has a problem with day 14. The further we go, the further it looks like a baby, we can get into trouble. So how do we solve that? Technical issues, this is unpublished data. We worked on mice. This is day 13.5 mouse embryos. That's as far as we went. But because we have a placenta, we can try to actually feed blood through the placenta and hopefully get them to grow bigger. This is not a priority for us, but that's first proof of concept. And then ethically, people talk about that, but for example, we did a CRISPR-Lim1 deletion in mice, and we got synthetic mouse embryos growing with no head, so with no brain. So it's an issue. We don't have the same thing for humans, but it's just show you where we can go to solve both technical and ethical issues. And again, we're going after real diseases. So even for hematopoietic stem cells, plastic anemia, graft versus host disease, we can go after real indication. It's a company, we have IP, both for creating the naive stem cells that are required to create the synthetic embryo, the hardware and reagent to create the synthetic embryo, and then we even have IP granted for stem cell-derived embryos, so we own it. And as for the team, Jakob, the professor, stayed in academia, but his entire team is working on that, all the IP is going to us, and this was so magical and important that I had to do it. But the most important team are on the right, a student at Jakob Lab that left to start companies and to do the postdoc. When they heard we're doing it, they came back together, so we got the all-star technical team back. So just a quick summary. We already raised $9 million. We can use way more. We believe it's a true breakthrough technology, huge implication for longevity and fertility, and we have the exclusive license. Also, our technical team, we built a lab already next to the Weizmann Institute in Israel, expand the team, did the tech transfer so it works, not just in Weizmann, it works around the world, including our lab. Our goal for this year is to get to day 35. We want to get to HSCs and go to the clinic with them, but and then next year, push as fast as we can. Go to later development stage so we can unlock more cells and more therapeutic area. And this is us, and thank you for listening.